Have you ever heard that saying, the whole is greater than the sum of its parts? Well, in medical science, that's not just a saying. It can be a serious warning. Today, we're going to crack open the statistical toolkit that scientists use to figure out when two separate health risks combine to create something much, much more dangerous. So, look, we all get that some things are risky for our health. That's pretty straightforward. But what happens when you start mixing those risks? If one thing is bad and another thing is bad, is the combination just double bad? Or is something else, something more complicated going on? That's the puzzle we're digging into. Let's make it real. Say smoking increases your risk for a certain condition by some amount, we'll just call it X. And maybe a certain medication increases that same risk by amount Y. So, what's the combined risk if you're a smoker who also takes that medication? Is it just X plus Y, or is it something else? This is exactly the kind of question researchers have to answer. So here's our game plan. First, we'll define what we even mean when we say more than the sum. Then we'll check out the two main tools scientists use to hunt this down, the comparison test and the prediction test. And we'll wrap it all up with a really powerful, real-world example that shows you exactly how this works. Okay, let's jump right in. When two risk factors team up and create an effect that is way bigger, or sometimes even smaller than you'd expect, scientists have a special term for it. They call it statistical interaction. All that really means is that the effect of one risk factor totally changes when another one enters the picture. They don't just add up nicely side by side, they actually influence each other, creating a brand new level of risk.
Right. So if researchers suspect an interaction is going on, how do they actually prove it? Well, it's definitely not a guessing game. They've got a specific toolkit they use, especially in what are called case control studies, which are studies that compare people with a condition to a similar group without it. And inside that toolkit, there are two main strategies. Two different ways of looking at the same data to see if that dangerous synergy is really there. Let's start with the first one.
So, tool number one is all about comparison. The technical name is homogeneity of effects, but don't let the jargon fool you. Homogeneity just means the same. So what scientists are asking is pretty simple. Is the effect of a risk factor the same for everyone?
The core question they're trying to answer is this. Does the risk from factor A look the same when it's all by itself versus when factor Z is also around? If the risk level from factor A suddenly jumps or plummets when factor Z shows up, well, that is a massive red flag that an interaction is happening.
And wow, check this out. This example makes it crystal clear. In a study looking at a heart condition, the risk linked to asthma for people without hypertension was a 2.4 odds ratio. But now look at people who also have hypertension. The risk from that same factor, asthma, skyrockets to 13.4. Those numbers are not even close to being the same. They are not homogeneous. That's a huge sign that asthma and hypertension are interacting in a powerful way. Now, this comparison test is fantastic for spotting a particular kind of interaction, what's called a multiplicative one. But, and this is a big but, it has a major blind spot in these types of studies. It can't be used to check for another really important type, known as an additive interaction. And for that, we're going to need our second tool. All right, on to our second tool. This one is really clever. It's all about making a prediction. Scientists basically calculate what the risk should be if the two factors were just minding their own business, and then they compare that prediction to what they actually see in the real world. And the process is just beautiful, simple logic. First, you measure the risk of just factor A on its own and the risk of just factor Z on its own. Next, you use a formula to predict what their combined risk ought to be. And finally, the big reveal, you compare that prediction to the actual observed risk you found in your data. If there's a big gap between what you expected and what you saw, bingo, you found an interaction. And this is where it gets really interesting, because scientists can make two different kinds of predictions. With the additive model, they just assume the risks add up. The formula is risk A plus risk Z, and then you subtract 1 to account for the baseline risk of people who have neither factor. The other option is the multiplicative model, where you assume the risks multiply. And as you can imagine, these two formulas can give you very different predictions. Okay, time for the main event. Let's take this prediction test and apply it to a classic, high-stakes example from a real study, the combined risk of heavy smoking and using oral contraceptives on heart attacks in women. So here's the data. Compared to women with neither risk factor, using oral contraceptives alone increased the odds of a heart attack by 4.5 times. Heavy smoking alone, that increased the odds 7 times. But, and here's the kicker, in the real world, the observed risk for women with both factors was a jaw-dropping 39.0. So let's run the test ourselves. Based on those individual risks, what should we have predicted the combined risk to be? Let's start with the additive model. Okay, if the risks were purely additive, our formula is 4.5 plus 7.0 minus that baseline of 1. That gives us an expected risk of 10.5. Got it? Okay, remember that number, 10.5. Now, what does the other model say? If the risks were multiplicative, we just multiply them. 4.5 times 7.0. That gives us a much higher expected risk of 31.5, a very different prediction. So let's see how both of these predictions stack up against what really happened. And here it is, the big aha moment. The additive prediction was way down here at 10.5. The multiplicative prediction got a lot closer, landing at 31.5. But the real observed risk was all the way up at 39.0. Look at the enormous gap between what the simple additive model predicted and what actually happens in the real world. That gap is the interaction. This massive difference led the researchers to one clear conclusion. There is a strong additive interaction. In plain English, the real risk was so much greater than the 10.5 you'd get by just adding them up. This isn't a case of 1 plus 1 equals 2. It's a case where these two risk factors got together and created a danger far beyond what you'd ever expect. So the prediction test is clearly a super powerful tool for uncovering these hidden dangers. But it's also important to know it's not foolproof. For instance, if a study is designed to match participants on a risk factor, like ensuring every case is matched with a control who is also a smoker, then you can no longer measure the independent effect of smoking. And if you can't do that, well, you can't run this test. And that's how it's done. That's how scientists look past the obvious to find those hidden connections where 1 plus 1 equals something much bigger. Which leaves us with a pretty important question, doesn't it? Now that you know how they spot these hidden dangers, what combined risks in our daily lives, our food, our habits, our environment, do you think need a much closer look? Thanks for joining me.